So here we go in the first of several videos we'll have for section 6.2. So this one, we're getting into some interesting things here. This is not just given a function and we integrate or find the area between two curves like we did in the last one. This section 6.2, which there are two separate assignments for this one because there's kind of a lot in it, and none of it is super easy at first. So what we're doing here is we're finding volume. We're using integrals to find volume of different shapes. And the shapes could be regular shapes, like a sphere or a cylinder, or the shapes could be irregular that come from graphing various functions. So just to kind of give an introduction and the way to think about this. So it says many three-dimensional solids can be created by revolving a region around a line. So what we mean by that, if you have a rectangle and you rotate the rectangle, you create a cylinder. If you rotate a triangle, then you create a cone. If you rotate a semicircle, then you can create a sphere. And so we're going to use this idea and the ideas that you learned in Calculus 1 when we started with antiderivatives and integration and finding area. So if you look here, we have the red is a circle. Now imagine, or probably even a semicircle if you can imagine a line going through there. So we have an upper semicircle, and imagine we rotate that around and we get a solid sphere. Now what happens with integration, and this we've seen this with just the two-dimensional graphs that you begin with in Calculus 1, where you cut a slice of that in a thin cross-section, if you will. And in Calculus 1, so if you have some graph or curve like this, then you cut it into different rectangles and you can find, they're equal width. You can find the height and then find the area of each rectangle. And probably when you start, you're doing something like this. You're getting an approximation, that kind of thing. So that's what's going on here with this circle that's turned into a sphere. We get cross sections and we find the volume of each cross section. We add up all the volumes together, and then that gives us an approximation for the volume of the sphere. And then, of course, as we get more and more sections of this, as we go up to infinity with the number of sections, then we get a more exact representation of the volume. So that's the idea. So we're going to use integrals to do this. The first way, and the method that we're going to talk about in this video, is called the disk method. Now, the shape up here is using the disk method. So we know what a disk is. A disk is just a solid round object. And so each cross section is a solid disk. The disk method is used when the solid has no hole in the middle. Each cross section is a solid disk, and I want you to think of it like a circle. And so we're finding the area. Imagine that each cross section is getting infinitesimally small, so it has no width, and we're just going to find the area of that disk when we rotate this graph around whatever axis we're looking at. And so the area of this cross section is going to be the area of a circle, which is pi r squared. Then we can add up all these areas, infinitely many of them, and that will give us the volume. And that's where we get the integral from a to b, pi times r squared. R is here as a function of x, because if you have a curve that looks like this again, and we're imagining that this is the radius. The height of this is going to be our radius. And now imagine we're rotating this around the x-axis. So we're taking this curve, we're rotating it around the x-axis. And so in reality, let's see if I can draw this upside down. Nope, didn't do very good there. Something like this. So just imagine this upside down. So now if we just take one little sliver of this, in 3 dimensions, that will be a circle because we've rotated this around. Okay? The radius of this circle that comes around like this is going to be the height of the curve. All right, so we basically doubled it if we go from top to bottom. The height of the curve from the x-axis to the curve will be the radius of that circle at that particular point. And then if we go here, we can see that the radius of this circle that we have when we rotate around this x-axis is going to be smaller. So the value of the function gives us that radius. And so we square that because pi r squared, the area of a circle, and we integrate from a to b, and then that gives us the volume of that shape that we get when we rotate around the x-axis. We can do the same thing with the y-axis if we're using this method, and we're going to get the volume, say now this. Let's try to draw this again. So we have this curve, and now we're going to rotate around the y-axis. And so we just kind of need a mirror image like that. And then just imagine this thing is coming around like this, and then it's going to come back around like that, and we get this 3-dimensional shape that's rotated around the y-axis. The y-axis is going straight through the center. So we integrate and we get the volume. All right. So that's the idea. I think probably after we do a few examples, you can come back and watch the beginning again, and maybe the idea will make more sense. Because some of these, and especially on the next homework, we're not going to be working so much with functions as we'll be shown a shape, and we have to find the volume of that shape without any functions. And so it's important to understand kind of the idea of this. And hopefully once we see a few of these examples, you can go back and watch this first part, and it will make a little bit more sense. Okay, so number 1, example 1, we're going to find the volume generated by revolving y equals square root of x from 0 to 1 about the x-axis. So you're going to need to be able to draw these graphs. So if you're not great, and I don't mean great at drawing it accurately, but you need to know square root of x looks like this. We are going from 0 to 1 and rotate it around the x-axis. So we're shading, here's our shaded area. Now we are rotating this around the x-axis. So, all right, so think of it going like this. And what is the volume of this shape that we end up with? All right, so what is the radius? So we have our volume formula. Now, I always pull pi out in front of the integral. It's not really doing much. You can just multiply your final thing by pi, and then that is it. So we are going from 0 to 1. Now, what is this distance? If we pick any random point between 0 and 1 and measure from the x-axis up to this curve, what is that distance? That distance is going to be the square root of x, whatever x is. All right, so we need to square that. So it's the radius function squared dx, and of course that's just going to be pi times the integral from 0 to 1. Square root of x squared is just going to be x. Now we integrate, and we get 1/2 x squared from 0 to 1. And of course, this is just going to be pi over 2. So pi over 2 is the volume of this when we rotate around the x-axis. All right. So it's important, first of all, in WebAssign, you're going to have to pick out the correct graph. So you're going to have to draw this graph whether you want to or not. But you should anyway. The important part of this is figuring out, find a cross section. It can be anywhere in your shaded area. How do you figure out what that distance is from the bottom to the top of the shaded area? So in this case, it's just the distance, whatever the y value of the function is. And so the y value of the function goes from 0 to 1, and wherever we are, it happens to be the square root of x. So that's the idea. All right, let's look at another one. So we're going to do the same thing. Now it's the region y equals x cubed from between y equals 8, x equals 0. Of course, y equals 0 also at that place. So let's draw this. And x cubed looks something like this. We're going to say y equals 8 is up here. So we got y equals x cubed. X equals 0, of course, is the y-axis. So now we have this shaded area completely enclosed like that. So now we're rotating around the y-axis. So we are rotating like that. So around this y-axis. Okay, so now what does this cross-section look like? So the cross-section always goes perpendicular to the axis of rotation. So in the last one, the axis of rotation was the x-axis. The cross-section is going to be perpendicular to that. In this one, the cross-section is going to be perpendicular to the y-axis. And so this was going to make us change this problem a little bit, because what is the distance? How do we find the distance from here to here? Well, we can't put x cubed because this is measuring y, not x. And so we need this one to measure y, not x. So let's rewrite this as x equals the cube root of y. All right. So now our volume, we have pi. We're writing this in terms of y. So in terms of y. So if you're rotating about the y-axis, you need to think of everything in terms of y. If you're rotating about the x-axis, you can think of everything in terms of x. Okay, so what is this distance from here to here? Now you could kind of turn your graph over if you like, and imagine this is the x-axis, and this would then be the cube root of x, if you like. You don't have to do that if you don't want, but the distance from here to here is the value of this function here. So the cube root of y. So the cube root of y, we got to square it because the radius is squared, and this is going to be dy. So pi, this is y to the 2/3, so we'll add 1, divide by the new exponent, and so 5/3 y, 3/5 y to the 5/3. Is that right? No, that's not right. That is right. Yeah, 2/3, add 1, we get 5. Okay, that is right. And then, we're going from 0 to 8 because we're on the y-axis, 0 to 8. So think we're moving this cross-section from down here all the way up the line. Okay. All right, so we get pi times 3/5 times 8 to the 5/3. So cube root of 8 is 2. 2 to the 5th is 32. 32 times 3/5 is going to be 96 pi over 5. Okay, so now as you can see, and as you work through these problems with the homework, the integration is not going to be hard. The hard part is going to be setting this up. Once you can get here, sometimes you got to be careful because you're gonna have a lot of fractions in this. But as far as integrating, it's not going to be too difficult. I mean, everyone should be able to integrate the cube root of y, or the cube root of y squared, or x, I think is what we had in the last one. So the actual integration is not the hard part. Hard part in the beginning will be figuring out how to get this set up. Okay, but I think most of the homework problems are pretty straightforward once you get the hang of this. So I would, however, recommend you go back if you have time, do the homework, but then go back and practice a little bit, because I don't know that the homework assignment's long enough to really get this just by itself. So okay, so now we have y equals 1 over x, x equals 1, x equals 2, y equals 0. So there's our region. We're rotating this around the x-axis, so that tells us that we will be working in terms of x. So 1 over x looks like this. We don't really need this part down here, so I won't worry about that. Let's call this 1, and let's call this 2. Y equals 0 is the x-axis, so we are looking at this. So now our cross-section goes perpendicular to the axis of rotation. So like that. And so now what is the distance of this radius? So we're rotating around the x-axis like this. So when we rotate this around, what is the radius, or what is that distance there? And so it's just going to be 1 over x, whatever x is. So our volume equals pi. We are integrating from 1 to 2. 1 over x squared dx. And so we have pi. This is 1 over x squared. The integral would be negative 1 over x from 1 to 2. So we have pi, plug in, we get negative 1/2, and then minus a negative 1, so that'd be plus 1. And then so we get 1/2 times pi, which is pi over 2. Okay, so there's the first few examples. When we get to the next part of this, we're going to look at what's called the washer method, which is very similar, but slightly different, not too much different. So I would probably say learn this one pretty good before you move on to the next one. Like try a couple on the homework and try to get this one down, then watch the next video. I don't think I'd watch, there's going to be 3 videos altogether. I don't think I'd watch all 3 of them just straight through. Watch one, do those problems, watch the next one, then do those problems. So it's kind of a lot to get used to. So try to take it in bite-sized chunks.